Okay, so in the previous lecture, we have already discussed process capability. We have already discussed that the different environment of sigma, standard deviation, 1 sigma, 2 sigma, 3 sigma, 4 sigma, and 6 sigma, and its role in the quality management. So now in this lecture, I'm just going to show you that how you will calculate Cp and Cpk manually and how you will use K1 macros in order to sketch a histogram, in order to sketch a normal distribution, and then point out the upper specification limit and the lower specification limit. So as I already mentioned in my previous slides, that Cp, basically Cp is very important in order to measure the dispersion, in order to check the process capability in 2 sigma, 3 sigma and 4 sigma. But one disadvantage of Cp that it doesn't measure the variation in the mean. In order to measure the variation in the mean, we will definitely use Cpk. So Cpk can never exceed Cp. Cp is just an upper bound for Cpa. So approximately 99.7% of the data from a normal distribution is contained between +3 minus sigma. So I have already discussed that when you sketch a normal distribution, it's mean that in 1 million, in 1000, let's suppose 997 part will be effective while 3 part will be defective. So if we sketch it, so you can see this is a interval, this is normal distribution which contain between 3 sigma. So the lower control limit and upper control limit lies between this yellow area is in the 3 sigma level. So it's mean that 997 out of 1000 will be in this portion, and there will be a chance of 3% that it will be outside from this region. If the process is in control and the distribution is well within the specification limit, then the difference between the upper specification and lower specification should be larger than 3 sigma. So as you know, we have already used this formulation in the previous lecture, that upper specs minus lower specs divided by 6 standard deviation. So basically this interpretation, the interpretation is given for this formulation. If the process is in control and the distribution is well within the specification limit, then the difference between the upper specification and lower specification should be larger than 6 sigma. So if the upper bound, if this numerator, if this upper specs minus lower specs value is greater than 6 sigma, then definitely the value will be high. So if the specification are larger than 6 sigma, the ratio will be less than 1. So if it is less than 1, then we will say the process is not capable. But if Cp is greater than 1, then the process has the potential to meet the specification as long as the mean is centered. So if the mean is not moving, if the mean set, the mean fixed, but if the variation in the dispersion, if the standard deviation value increase, then it will not affect. We can easily calculate Cp and we can easily rely on Cp. If the value of Cp is 1, then we will say, or if it is greater than 1, then we will say that the process is potential, the process is capable. If Cp value is approaching to 2, then we will say that the process has the potential to meet the 6 standard deviation. If it is near to 1 or if it is near to 1.5, let's suppose, so we can also say that the process is capable and it meets 4 sigma and 5 sigma specification level. So you can see from this figure that the lower specification limit and upper specification limit. So most of the area is outside of the specification limit. So I mean visually we can see that this process is not capable. Okay. So from the figure you can easily see, because this area is only, so it's mean the process is only capable for 1 standard deviation. It's not capable for 2 standard deviation, 3 standard deviation or 4 standard deviation. In order to check it, you can easily calculate Cp value. So upper specification is 0.048 minus lower specification is 0.042 divided by 6 standard deviation, and standard deviation value is given to you. So you can see the value is 0.19, which is much lesser than 1. That is why the process is not capable for these. So you can also see from the figure that most of the area is outside, the dispersion is outside, most of the bar of the normal distribution is outside from the upper and lower specification limit. Similarly, you can see now this is a little bit different from this. The dispersion is same, but our upper specification limit is this one, 0.06, and the lower specification, the mean is set, the mean is same. The standard deviation of this and the standard deviation of this is same. The mean is also same. But the upper specification limit and lower specification limit of this one is different and this one is different. So we can easily identify that most of the area is inside. So you can say that process is capable. And how you can say this? Because the Cp value calculated from these parameters, it is approaching to 0.97, which is near to 1. So you can say that the process, there is some area outside, you can see with these two asymptotes. But you can say that this process is more or less capable for 3 sigma. But it's not capable for 4 sigma, 5 sigma, 6 sigma. Because in my previous lecture, I already mentioned, if Cp value is approaching near to 2, then in that case, you can say that it is capable for the 6 sigma, 5 sigma, because those 4 or 5 sigma are the very high quality parameters. So at this way you will calculate Cp. So now another parameter which is called Cpk. Cpk is a process capability index that assesses how close the process mean is from the specification limit. So normally our standard deviation is same, but the deviation dispersion is same, but our mean is not mean. For example, I will shortly give you a simple example. I will feed a video in which you will see an example of the coffee machine. In that coffee machine, at first instance we will calculate Cp. So in that Cp our mean will be fixed. But when the machine getting older, so normally at 50 centigrade, let's suppose, it make your coffee. But when the machine going older, then maybe the mean will be changed. Normally it will take 51 or 52 centigrade in order to prepare your coffee. So in that case, now the mean is moving, the standard deviation is same, the dispersion is same. So in order to measure such like process, in order to capture the variation in the mean, you will use Cpk. Cpk is a process capability that assesses how close the process mean is from the specification limit. So in this one we will check the mean, and in the other one we will check the dispersion. If the process is in control and the distribution is well within the specification limit, then the difference between the upper and the mean or the difference between the lower and the mean should be larger than 3 sigma. So this is the interpretation of the Cpk formulation. Cpk formulation, I will show you that how you will calculate Cpk manually in some example in the later slide. If Cpk is greater than 1, then the process mean is sufficiently far from the specification limit. So you can see that in this example, in this figure, our upper specification limit is this one and lower specification limit is this one. So most of the area is outside from the specification limit. So we can say that this process is not capable, because when you calculate upper, so upper specs minus x, the mean, divided by 3 sigma. This is the formulation for Cpk for the upper. So when you calculate this, upper specs is this one, upper specs is 0.048 minus 0.045 divided by 3 into 0.05. So you will get this value 0.22. So 0.22 is much lesser than 1. So the process is not capable. Now CPL, which is this one is the upper, this one is the lower process capability index, okay, Cpk. So X double bar, the formulation is different from this one. X double bar minus lower specs divided by 36 sigma. So when you calculate this, you will get CPL 0.17. Okay. Now we want to calculate Cpk. So the formula of Cpk is minimum of CPL and CPU. So you will choose the minimum of both these two. So this value, CPU value is 0.22 and CPL value is 0.17. So which one is the minimum one? The minimum one is 0.17. So Cpk is less than 1. The process is not capable. So there is some more interpretation. When Cpk greater than 1, which show that the process is probably centered and usually able to meet specification. So you need to remember this. When the value of Cpk is greater than 1, then we will consider that the process is capable. Is it central? The mean is in the central. Cpk less than 1 indicate either the mean is not centered between the specific, or there is problem with reliability. So there are two main causes. If Cp is less than 1, so there are two causes. Maybe the one cause is that the mean is not centered. Mean is deviating. Mean is changing position, or the variability of a change. Mean One time your coffee machine make your coffee at 50 centigrade, but on the other time it requires 55 centigrade. When the heat reach to that level, it will prepare your coffee. So CPK mean is mean to be used with process that are in control, give us a measure of whether the in control process is capable of meeting specification. So CPK is not appropriate measure if there are trends, runs out of control observation, or if the process is too variable. So the most important thing in the drawback or disadvantage of CPK, if there is some fluctuation in the data, if the data is not a refined one, if the data is not so smooth, then CPK parameter, CPK result will not be so good. Okay, so you in that case you need to construct a histogram, you need to construct a normal distribution, and then after that you will be able to check the behavior of the data. So in this case, in this slides, you can see that when Cp is less than 1, as in figure B, in this one, process not capable of producing within specification. When Cp is greater than 1, as in figure C, you can see this one, a process exceed minimal specification. So most of the area upper and this is lower. But in this case, most of the area is out, because in this case Cp is less than 1. In this case Cp, this is your upper and this is your lower. So the whole histogram is inside. So that is why the process exceeds minimal specification. And Cp is greater than 1. So the process is capable. One shortcoming Cp assume that the process is centered on the specification, when Cp is equal to Cpk when process is centered. So when the mean is not changed, if the mean of a distribution is same, so the value of Cp and Cpk will be same. Okay, but if the mean change their position, if let's suppose now in this example, in this figure mean is 16. Okay, if mean is same, so for this Cp and Cpk value will be same. But if this mean change, let's suppose it changed from 16 to 16.1, then in this case Cp and Cp will not be same. Cpk never exceeds Cp. Remember this. And Cp is just an upper bound for Cpa. Now I'm just going to show you a simple discussion in a short video.
Process capability in terms of 3 sigma, 4 sigma, 5 sigma and 6 sigma levels. Another important way to express process capability is in terms of a measure known as the process capability ratio, denoted by C subscript P. Cp can be calculated using the formula shown. Think about this calculation as a question. We are looking at the range of the customer's tolerance, that is, upper specification minus lower specification. The question we are asking is, within this range, can we fit 6 standard deviations? If we can do that, then our answer will be greater than or equal to 1, and we say the process is capable. If we cannot do that, our answer will be less than 1, and we say the process is not capable. How does this Cp measurement line up with the scale we saw earlier in terms of 3 sigma, 4 sigma, 5 sigma, and 6 sigma levels? To answer that question, let us look at our 3 sigma capable coffee machine, Model A. This machine is able to produce coffee at an average temperature of 160 degrees, with a standard deviation of 3.33 degrees. Within our desired range of 160 plus or minus 10 degrees, we are able to fit 3 standard deviations on either side of the mean. Calculating the Cp, we get 170 minus 150 divided by 6 times 3.33, which comes to 1.0. Imagine we have a custom designed ruler that we are using to measure our process variability. Instead of being marked in inches or centimeters, this ruler is marked in standard deviations. The ruler itself is 6 standard deviations long, so say we call it our 6 standard deviation ruler. Looking at the Cp calculation as a question, can we fit 6 standard deviations within the range of our customer's tolerance? The answer is yes. Our 3 sigma process is capable of giving us what we want, but it is at the bottom of our process capability scale. Let us now look at our 4 sigma capable coffee machine, Model B. This machine is able to produce coffee at an average temperature of 160 degrees with a standard deviation of 2.5 degrees. Within our desired range of 160 plus or minus 10 degrees, we are able to fit 4 standard deviations on either side of the mean. Calculating the Cp, we get 170 minus 150 divided by 6 times 2.5, which comes to 1.33. For this process, our 6 standard deviation ruler is a little shorter than for the previous one, because the standard deviation here is a little smaller. Looking at the Cp calculation as a question, can we fit the 6 standard deviation ruler within the range of the customer's tolerance? The answer is yes. In this case, we can fit the ruler not just once, but also a third more. That is what the Cp value of 1.33 implies. We have moved up a notch on our process capability scale. Let us now look at our 5 sigma capable coffee machine, Model C. This machine is able to produce coffee at an average temperature of 160 degrees with a standard deviation of 2 degrees. Within our desired range of 160 plus or minus 10 degrees, we are able to fit 5 standard deviations on either side of the mean. Calculating the Cp, we get 170 minus 150 divided by 6 times 2.0, which comes to 1.67. For this process, our 6 standard deviation ruler is even shorter. Looking at the Cp calculation as a question, can we fit the ruler within the range of the customer's tolerance? The answer is yes. In this case, we can fit the ruler not just once, but also 2/3 more. That is what the Cp value of 1.67 implies. We have moved up another notch on our process capability scale. Let us now look at our 6 sigma capable coffee machine, Model D. This machine is able to produce coffee at an average temperature of 160 degrees with a standard deviation of 1.67 degrees. Within our desired range of 160 plus or minus 10, we are able to fit 6 standard deviations on either side of the mean. Calculating the Cp, we get 170 minus 150 divided by 6 times 1.67, which comes to 2.0. For this process, our 6 standard deviation ruler is much shorter, half the length of the original ruler. Looking at the Cp calculation as a question, can we fit the ruler within the range of the customer's tolerance? Yes. In this case, we can fit the ruler not just once, but twice. That is what the Cp value of 2.0 implies. We have moved up to the upper end of our process capability scale. Meanwhile, how does my current 2 sigma capable coffee machine measure up on this ruler? This machine is able to produce coffee at an average temperature of 160 degrees with a standard deviation of 5 degrees. Within our desired range of 160 plus or minus 10 degrees, we are able to fit only 2 standard deviations on either side of the mean. Calculating the Cp, we get 170 minus 150 divided by 6 times 5, which comes to only 0.67. For this process, our 6 standard deviation ruler is rather large. Can we fit the ruler within the range of the customer's tolerance? The answer is no. In this case, we can only fit 2/3 of the ruler. That is what the Cp value of 0.67 implies. We have dropped below the capable range of our process capability scale. The process capability ratio, Cp, thus provides us a process capability scale that goes from 1.0 to 2.0. Processes that are less than 3 sigma capable would be considered as not capable. The 3 sigma, 4 sigma, 5 sigma, and 6 sigma levels of process capability correspond to Cp values of 1.0, 1.33, 1.67, and 2.0. These process capability scales increase in a linear fashion. However, the corresponding process quality levels increase astronomically. Let us go back to the 4 sigma capable coffee machine, Model B, with an average temperature of 160 degrees and a standard deviation of 2.5 degrees. The Cp value for this 4 sigma capable process is 1.33. Now let us say the temperature knob on this machine has become loose over time. I set the knob at 160 degrees, but the machine is actually producing coffee at an average temperature of 162 degrees. Let us calculate the Cp again. The upper and lower specifications are still 170 and 150 degrees, respectively. The standard deviation is still the same at 2.5 degrees. Therefore, Cp works out to 1.33. Wait a minute, that's the same value as before the process shifted upwards, isn't it? But clearly the process is not capable at the 4 sigma level anymore. We are now unable to fit 4 standard deviations between the process mean and the customer's upper tolerance of 170 degrees. But our Cp value has not changed to reflect that fact. The Cp measure only tells us whether the variability of our process is adequately small. It does not take into account whether our process is off-center. There is another important measure of process capability that takes the process centering into consideration. This measure is known as the Process Capability Index, denoted by C subscript pk. Cpk can be calculated using the formula shown. Think about this calculation also as a question, but as a two-part question. Each part of the question looks at how far the process mean is from one of the ends of the customer's tolerance range. For Cp, we were trying to fit a 6 standard deviation ruler 1.33 times within the entire customer's tolerance range. 1.33 corresponds to 4 sigma. For Cpk, we are trying to fit a 3 standard deviation ruler 1.33 times on each side of the process mean. If the process mean is closer to one of the edges of the range, we have less room on that side, so that side will limit our process capability. Calculating the Cpk, we see that the upper and lower specifications and the standard deviation are the same as for our Cp calculation. However, the process mean has shifted to 162 degrees. We can fit the 3 standard deviation ruler 1.6 times between 150 degrees and 162 degrees, but only 1.067 times between 170 degrees and 162 degrees. The Cpk value is the smaller of these two numbers, or 1.067. An interesting point to note here is that the average of 1.6 and 1.067 works out to 1.33, which is our Cp value. If the process were to be centered at 160 degrees, then both parts of our Cpk calculation would work out to 1.33, and Cpk would equal Cp. Thus, Cpk can never exceed Cp. Cp sets the upper bound for Cpk.